this list and make it much better. But it is one of my favorite things to think about. Okay, so moving deeper into the evolutionary ecology issues, how does immunopathology as a cost of immunity fit alongside other costs? So this comes from Paul's new book, kind of a taxonomy of costs of immunity, where you can think of costs of having an immune system on the one hand, and the costs of using it on the other. And in each category there are genetic as well as physiological costs. The stuff I'm talking about really is over here in the deployment area. And I was very curious, the moment I got this book, to see where Paul would put immunopathology, and he certainly puts it in the deployment zone, right next to physiological costs, physiological being the ones that are subject to allocation. For example, individual organisms allocating differently to manage the cost-benefit ratios. I was just thinking about this, like, does he think it's quite separate from physiology? And then I read in the legend, self-reactivity is strictly speaking a physiological cost too, however it is perceived distinct enough to warrant its own category. So I was completely in agreement that it seems like it might be different, but I think we don't actually know yet. I think it seems sensible that both edges of the sword require energy, for example. So if there is any sort of, if mammals, for example, are energy limited and immunity is energetically costly, both the resistance types of immune responses and blasting holes in your own cells are going to potentially be energetically costly, right? So for that reason alone, it seems like these do need to have some sort of grouping, but exactly what the relationship between them is not yet clear, and I hope for lots of clarity over the next couple of days in discussions at this meeting. I told you that part would be short. Okay, so now for the real meat of what I want to say about immunopathology. Some recent work to try to understand why it might matter evolutionarily, and perhaps the context in which it might matter. And this is where both theory and empiricism come in, and Troy has been the key theoretician I've been working with on this, and Grania, the empiricist. So they are the stars of this set of results. Okay, so Troy's not long been interested in the cost of immunity, but he hasn't worked on it a lot, per se. He comes more from the parasite virulence evolution angle in general. And so our approach has been to take classical evolutionary epidemiology theory that has been successfully used to understand the evolution of parasite virulence and bring in the double-edged sword. Basically adding immunopathology in a fairly explicit mechanistic way, as you'll see, into that framework to understand effects on parasite evolution. And we've published that one, and I'll show you one result from that. One that we haven't yet published, it's in prep, is to put that same immunopathology into the host evolutionary model, and also potential for energetic costs separately for now, and to then try to understand the effects on host evolution. And then we decided to go all out and add coevolution too. So this is a beginning step to try to build immunopathology into this framework, and because we also wanted to make it sort of mechanistically understandable, or at least quasi-accessible to empiricists, we're having to take a lot of baby steps with our assumptions. And so what we've done is to what Troy really did. He's the main guy on this, as I said, and I will be able to answer a limited subset of the questions you might ask me about this. I'll do my best. So cost of immunopathology we've built in the currency of survival. Basically, there's some mortality that's due to parasite virulence, direct parasite-mediated damage. But what we've done is we have an additional mortality cost of mounting an immunopathological response of that tissue damage. The cost of resistance, however, is built into host reproduction. And so I think this is to some extent defensible, but probably the pure separation, the way it's done, isn't optimal. And I'd love any feedback on that. However, there is quite a lot of precedent in thinking about that one, right? And a fair bit of empirical evidence. Just quickly to show you the empirical evidence I was associated with collecting most recently, is that antibody responsiveness is positively associated with survival. So in this case, there might be a protective immune element, but negatively associated with annual reproduction in the cell age sheet. So this is just showing with increasing antibody responsiveness on the x-axis, probability of breeding success year on year is reduced in both males and females, with some complexities to do with maternal antibody transfer, we think. Anyway, just wanted to say that I do think we have some good reason to build any application, energetic costs of immunity into the reproduction enrollment. But perhaps there does need to be some crosstalk there. The other key assumption is sterilizing immunity, because we had to assume basically that it was a measles type infection in this theoretical context, which of course is the exception, not the rule. However, it is a starting point. Okay, so here's how we made the model quasi-mechanistic. So we conceived it as a linear statistical model, basically, this component of the theory. So this is the term describing the additional mortality arising from immunopathology. So this is that mortality cost of immunopathology. And basically, we conceived of this as a linear statistical model where we're really interested in the coefficients here, these fees. Epsilon is the exploitation strategy of the parasite. And so you can think of P1 as being that component of immunopathology that scales with what the parasite is doing, parasite density, for example. Because it's reasonable to think that some immunopathology does occur on a per parasite basis. Each additional parasite flicking a toll-like receptor, for example, plausibly would increase the expression of immunopathology. So that's what P1 is about. C is the clearance rate. Again, these are terms straight out of virulence evolution theory, so if any of you are aficionados, this should look familiar. C is the clearance rate, so the rate at which the host gets rid of the parasites, and we expect that to increase with increased immune activation. So for example, hosts with a really high recovery rate, or clearance rate rather, should have really high induction of inflammatory mediators. They might be the cytokine stormers. So Phe2 captures the dependence of immunopathology mortality rate on clearance rate. And then we have the independent, the term that's independent of both, and then we have the interaction term. So it's really kind of a straightforward ANOVA type way of thinking about how immunopathology is generated. And it turns out it's important, it seems to be important to break it down that way. Just for further Greek, people with interest in Greek, I just wanted to point out that we were able to derive terms for both parasite fitness and host fitness. And what the left side here in each case is the sort of classic evolution of virulence approach, meaning in a world without immunopathology assumed. And then we were able to, with only minor modifications basically to the death terms in each case. So again, all we've done is build in the mortality cost of immunopathology into the denominators on the right. Okay, so this is the result for optimal strategies of parasites, just to help orient you and also give you some reading material since if you're interested, just because we don't have that for the host side yet. But these are the optimal parasite exploitation strategies. Remember, epsilon is the parasite strategy that might include how much to proliferate, that sort of thing. And then pathogen fitness on the y-axis. And so in a world without immunopathology, which I call IP sometimes under Troy's influence, I think he found it had too many syllables. So you know, the man who generates Greek like this wanted IP to have only two letters in the acronym. But anyway, I can sympathize. But here's a world without immunopathology. The optimal exploitation strategy to maximize parasite fitness is there. And what was interesting is that in a world with immunopathology, depending which way immunopathology arose, can either reduce or increase the optimal virulence of the pathogen. So for example, if immunopathology is independent of exploitation, so basically if Phe3 and Phe1 are both 0 essentially, and those terms drop out of the model, such that either all of the immunopathology is completely independent of what the parasite's doing, independent of what the host's recovery rate is. This is the kind of thing like if, the immunoprivileged sites potentially, right? A single mistake in the brain can be lethal, right? That's the idea, is that this is capturing that kind of additional mortality. Anyway, so if immunopathology is independent of exploitation, one or both of those terms is non-zero, then that actually increases the optimal exploitation strategy of the parasite. It basically functions like additional background mortality. So parasites just need to get out of there, essentially. On the other hand, if immunopathology increases with exploitation, so if each parasite is causing that little bit of extra immunopathology, then the prediction is quite different. The optimal level of parasite virulence is expected to decrease. So when a similar framework is applied to host evolution, again leaving this up here for reference in case the statistical framework helps you think about it, we found that it can alter the optimal strategy for host 2, and then again, the mechanism by which immunopathology arises matters. So in this case, the two circled terms are the ones that are depicted here. Basically, strength of immunopathology increasing of each type on the x-axis, and then the evolutionary stable strategy for recovery on the y-axis. And the dashes and solid lines and things are just titrating in and out how much of the mortality is due to immunopathology. And you'll see that the shapes of the curves are affected by it, but sometimes it's a bit subtle. Like, for example, if actually for infections where most of the mortality is due to parasites directly rather than immunopathology, then adding in immunopathology doesn't change much about the evolutionary stable recovery, that makes good sense. When, on the other hand, in diseases where most of the mortality is due to immunopathology, there can be quite a potent effect of increasing that sort of that completely independent, maybe anatomical location related type of immunopathology. It actually, as that increases, then hosts should invest more and more in recovery rate actually, because the sooner they clear that thing, the sooner the risk of death is obviated. In the case of this one that scales with clearance rate, the more collateral damage per unit of investment in recovery, then the lower evolutionary stable strategy recovery rate. So again, you come up, depending what parasite or pathogen you're thinking about, you might end up with quite different predictions of what the evolutionary trajectory should be in a world with immunopathology. And just to completely boggle, not really, but coevolution, of course, is very complex. But there were some really interesting things that came out of it. For some reason, there were supposed to be some points on here, but anyway, the main point is clear. So this is now a coevolutionary plot where the evolutionary stable host strategy is on this axis, evolutionary stable parasite strategy on this axis, and basically that hidden thing I haven't shown you any equations for, but the cost of